Could nuclear rockets be the key to getting humans to Mars? The faster you can get a crew to Mars, the better, but conventional propulsion systems may not be up to the task. NASA plans to send crewed missions to Mars over the next decade, but the 140 million mile journey to the red planet could take several months to years to round trip. This relatively long transit time is a result of the use of traditional chemical rocket fuel. An alternative technology to the chemically propelled rockets the agency develops now is called nuclear thermal propulsion, which uses nuclear fission and could one day power a rocket that makes its trip in just half the time. Nuclear fission involves harvesting the incredible amount of energy released when an atom is split by a neutron, and this reaction is known as a fission reaction. Fission technology is well established in power generating and nuclear-powered submarines, and is applicable to drive or power a rocket, could one day give NASA a faster, more powerful alternative to chemically driven rockets. NASA and the Defense Advanced Research Project Agency, DARPA for short, are jointly developing NTP technology. They plan to deploy and demonstrate the capabilities of prototype system in space in 2027, potentially making it one of the first of its kind to be built and operated by the US. Nuclear thermal propulsion could also one day power maneuverable space platforms that would protect American satellites in and beyond Earth's orbit, but the technology is still in development. Nuclear versus chemical propulsion. Conventional chemical propulsion systems use a chemical reaction involving a light propellant such as hydrogen and an oxidizer. When mixed together, these two ignite, which result in propellant exiting the nozzle very quickly to propel the rocket. These systems do not require any sort of ignition system, so they're reliable, but these rockets must carry oxygen with them into space, which can weigh them down. Unlike chemical propulsion systems, nuclear thermal propulsion systems rely on nuclear fission reactions to heat the propellant that is then expelled from the nozzle to create the driving force of thrust. In many fission reactors, researchers send a neutron towards a lighter isotope of uranium, uranium-235. The uranium absorbs the neutron, creating uranium-236. The uranium-236 then splits into two fragments, the fission products, and the reaction emits some assorted particles. More than 400 nuclear power reactors in operation around the world currently use nuclear fission technology. The majority of these nuclear powered reactors in operation are light water reactors. These fission reactors use water to slow down the neutrons and to absorb the transfer heat. The water can create steam directly in the core or in a steam generator, which drives a turbine to produce electricity. Nuclear thermal propulsion systems operate in a similar way, but they use a different nuclear fuel that has more uranium-235. They also operate at a much higher temperature, which makes them extremely powerful and compact. Nuclear thermal propulsion systems have about 10 times more power density than traditional light water reactor. Nuclear propulsion could have a leg up on chemical propulsion for a few reasons. Nuclear propulsion would expel propellant from the engine nozzle very quickly, generating high thrust. This high thrust allows the rocket to accelerate faster. These systems also have a high specific impulse. Specific impulse measures how efficiently the propellant is used to generate the thrust, and nuclear thermal propulsion systems have roughly twice the specific impulse of chemical rockets, which means they could cut the travel time by a factor of 2. Nuclear thermal propulsion history. For decades, U.S. government funded the development of nuclear thermal propulsion technology. Between 1955 and 73, programs at NASA, General Electric, and Argonne National Laboratories produced and tested 20 nuclear thermal propulsion engines, but these pre-1972 designs relied on highly enriched uranium fuel. This fuel is no longer used because of its proliferation dangers or dangers that have to do with the spread of nuclear material and technology. The The Global Threat Reduction Initiative, launched by the Department of Energy and National Nuclear Security Administration, aims to convert many of the research reactors employed highly enriched uranium fuel to high assay low enriched uranium, or HALEU fuel for short. High assay low enriched uranium fuel has material capable of undergoing a fission reaction compared with highly enriched uranium fuel, so the rockets need to have more HALEU fuel loaded on, which makes the engine heavier. To solve the issue, researchers are looking into special materials that would use fuel more efficiently in these reactors. NASA and the DARPA's demonstration rocket for agile cislunar operations, or DRACO for short, the program intends to use this high assay low enriched uranium fuel in its nuclear thermal propulsion engine. The program plans to launch its rocket in 2027. And as part of the DRACO program, the aerospace company Lockheed Martin has partnered with BWX Technologies to develop the reactor and fuel designs. Ongoing research. Before engineers can design an engine that satisfies all these standards, they need to start with models and simulations. These models help researchers such as those in my group, says the writer, understand how the engine would handle starting up and shutting down. These are operations that require quick, massive temperature and pressure changes. The nuclear thermal propulsion engine will differ from all existing fission power systems, so engineers will need to build software tools that work with these new engines. Now, my group, he says, designs and analyzes nuclear thermal propulsion reactors using models, and we model these complex reactor systems to see how things such as temperature changes may affect the reactor and the rocket's safety. But simulating these effects can take a lot of expensive computing power. We've been working to develop new computational tools that model how these reactors act while they're starting up and operating without using as much computing power. My colleagues and I hope this research can one day help develop models that could autonomously control the rocket. And this is from the conversation by Dan Kotliar, Associate Professor, Nuclear Radiology Engineering, Georgia Institute of Technology, on Unexplained Mysteries. Please leave your comments, and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.